especially because I'm not a theorist. However, there have been recent developments in string theory which have an overlap with the kind of things I do. I mean, I do lattice QCD. This is not QCD, but have an overlap with statistical mechanical models and lattice calculations. So thanks to my colleague, Professor Anindo, who got me interested in this. And thanks, of course, to two very hardworking students, Atul Sharma, who was a UG, he has now graduated, and Anirudh Venkat, who's going to be spending the summer with us at IISc. He's actually from HBCSE in Mumbai. Thanks to all of them, we've actually begun looking, and the thing we are looking at is verifying, as the title describes, verifying the predictions of conformal bootstrap through lattice calculations. So, conformal bootstrap theory, I guess I don't really, I mean, I'm not in conformal bootstrap theory. You guys would know it much better than I do. But as I say, you have thermodynamic systems. Very often they show all but the simplest thermodynamic systems. They have well-defined phase transitions, and this transition could be first order or second order. Second order transitions are actually quite distinct from first order transitions in the sense that different systems, very different systems, tend to fall into universality classes. And this is something you would all know from your StatMech studies. Because of this, very different systems tend to show very similar behavior near the phase transition. And that's actually because at the critical point, and close to this critical point, you start having fluctuations which show up at all length scales. And these fluctuations, they tend to grow to macroscopic length scales. So the microscopic details of the Hamiltonian don't matter so much anymore. And it was known that this system actually becomes scale invariant at the transition point. It has also been conjectured that these systems are conformal invariant, not just scale invariant. Scale invariance is a subset of this whole conformal group, but they're actually conformal invariant at the critical point. This actually, I'm sorry, this is not quite correct. This was known for quite a long time for the two-dimensional Ising model, and recently, a few years ago, it has been rigorously demonstrated even for the case of the 3D Ising model. For all models more difficult than this, remains a conjecture. And the thing is, conformal invariance is a very powerful, it's a very powerful statement. So it actually imposes very stringent conditions on, for example, these correlation functions of operator. And in particular, for example, it fixes the 2-point. Actually, I've put it as this tilde here will always stand for up to proportionality constants. But really, it fixes this 2-point function to be exactly the difference falling off as a power. This power is actually known as the anomalous dimension of this field. And the other thing that happens due to conformal invariance is you have a 4-point function. All higher order n-point functions can actually be calculated once you know the 2 and 4-point functions. So it really generates a series of recursion relations which you can calculate any n-point function. The 2-point function always has this form in any dimension. Any dimension. However, for 4-point function, it's not easy to get a closed form expression. In fact, for 3 and higher dimensions, you only get an expression in terms of a series, an operator product expansion. However, for 2-point functions, this result is known exactly. And it's somewhat complicated looking, but once you get more and more familiar with it, you realize it's not so complicated. If, for example, one tends to define these two ratios, u and v, and actually, due to conformal invariance, you find that this 4-point function, you pull out a leading power law dependent, and everything else can be expressed entirely in terms of u's and v's. The fact that you can express things in terms of ratios is actually a statement of a scale invariance or conformal invariance. Anyway, this this power law, I mean, so there is still nevertheless a leading power law fall off. And what happens is if I take this limit in which these points, I bunch them to two groups of 2, then in some 4 just function of a composite operator phi squared. And now what happens is all that survives when I do this bunching, for example, u goes to 0 and v goes to 1. Sorry, I'm sorry. U goes to 0, root 2 cancels this root 2, and what you just have, and since 1 goes to 3 and 2 goes to 4, this also becomes a square. So you have a leading power law fall off of 1/2, and this can be taken as the composite operator phi squared. So basically, I mean, these are, I mean, some of the ways in which you can extract anomalous dimensions operators. What we will be doing is we will actually be verifying. So what has happened is in conformal bootstrap, string theorists actually come up with a lot of predictions. It's not just these anomalous dimensions, but when you expand this in a series, for example, the prefactor, the coefficient multiplying each operator, the OPE coefficient, there are lots and lots of predictions for all of these. And we got into this, I got into this because, we wanted to know if, we can verify at least a subset of these predictions. These are not easy to get such high accuracy with Monte Carlo calculations, but we could at least a subset of these predictions doing Carlo. Another interest in this whole game is that there is a vast and ongoing, and scalar field theories and so on, and so this was a kind of my field. So a quick word about the Ising model. I don't think I really need to introduce the Ising model. The simplest CFT that, which belongs to the Z2 universality class, the symmetry group is Z2. So for that, you can just simulate the Ising model. We know its critical temperature, we actually know its critical exponents and everything very well. In fact, even analytically in most of the cases. So this was the model, and you have a partition function which you want to numerically simulate in order to extract observables of interest. So here's the problem. I mean, so it seems like, all one has to do, you have to just put it on a reasonably powerful computer. Sometimes, even desktops are good enough for something as simple as an Ising model. So the question is, where, I mean, is it really something difficult, or can we be done by tomorrow? And the problem is actually that, it has a second order phase transition at a temperature Tc, some temperature, and as you get closer and closer to the second order transition, the correlation length of the system, it starts to grow more and more. And so at some point, as you start getting closer and closer to Tc, the correlation length, it diverges, and it's already like of the order of 1000 or so, and the exact transition temperature is actually 2.269 something. So already by the time you're like reasonably close to Tc, correlation is very large. So an exponential off of a correlation, you have to go to something larger than this. So I mean, that's really the challenge. I mean, with our current attempts, we can't really go beyond something like, let's say, 1000 or 1200, but that also sets a limit to how close to Tc you can get, which in turn means that there's always some systematic error in your calculations. Anyway, this problem is actually not just specific to two-point correlators. People have known this for quite some time. You would all know the standard thermodynamic observer, like the magnetic susceptibility diverges as the reduced temperature raised to minus gamma, where gamma is a critical exponent and so on. And people already knew that, you cannot do such high res studies, literally see a power kind of fall off. So even if you had the computing power, one should try to do somewhat better. And so there's a whole theory called finite-size scaling, which has developed to actually so that one can work at smaller lattices and not necessarily too close to Tc. And let me just illustrate this by first applying it to the magnetic susceptibility. So here's the thing, I mean, as you know from your StatMech lessons, on an infinite lattice, in infinite volume, the magnetic susceptibility diverges. T is the reduced temperature here, T minus Tc by Tc. Since T itself is, a function of the correlation length, you can actually write it like this. Susceptibility on a finite lattice is given by this leading power law behavior times a function. This function accounts for finite lattice corrections. That I write something which is actually a function of L comma psi as L by psi is in some sense RG prediction. It says that everything, the close to criticality, all scales are set by this correlation length xi. What happens is if and closer to Tc, xi starts to diverge. So it that this must saturate. Instead of diverging on a finite lattice, your magnetic susceptibility must diverge. So based on these limits, you can actually pull out various limiting behaviors of this function. It goes to a constant if L is very large, much larger than xi, and if xi is much larger than L, it removes this leading order divergence and saturates the function. So that's exact as far as the mathematics goes, but xi is typically not easy to determine. So what we do is we just replace xi by, we can trade xi for t and define some new variables. So just do some standard jugglery. You can define an f instead of an f tilde and an x instead of an x prime. You get something like this. You get an equation like this. And note that I have now pulled out the divergence, and replaced the divergence in terms of the lattice size. So what it means is that on different lattices, I find that it sort of scales with increasing L. And if I take this to the other side, if I take L to the gamma by nu and multiply it with chi, all I have on the right hand side is a universal function. So in other words, for all lattice sizes, if I plot L to the gamma by nu chi versus L to the 1 by nu times t, it should just give me the same curve for all. And this is an illustration I've pulled from a textbook, and you can see that you have lattices going from really tiny, 10 by 10, all the way up to 200 by 200. And it's really nice to see how they all fall on just one universal, underlying curve. You see, as you go really far away, non-universal correction start to show up. And that's why this thin band sort of starts to spread out. But you really have, let's say, from about -4 to 3 maybe, you really have what is called curve collapse. But note that, for curve collapse to occur, you actually need to use the right values of, gamma nu and as well as, Tc. So in some sense, FSS can be used to, determine if you don't know it a priori, or if you have some predictions, you can use it to verify the critical parameters of a theory. The x-axis is this L to the 1 by nu times. The y-axis is L to the gamma by nu times the magnetic susceptibility. So all you have on the right-hand side is one function, which is some, this underlying function. Anyway, the thing about FSS is instead of, close to the origin, you will have the scaling law you want, but actually FSS gives you a function for a much wider range of the variables. So it's not necessary to work with very large lattices or be too close to Tc. So what we did is, what I did with Atul and Anirudh was we said, okay, fine, we want to try something like this, but we want to extend it now for a correlation function. It's not a bulk observable, it's a correlation function. So let's play the same game. One addition is now that there is a position dependence. It depends on a variable r. So if I want to really replace it as before, I pull out the leading dependent. This is the CFT prediction. E is power law fall off. But then I pull it out as, I write some underlying universal function, which is now a function of r by xi and L by xi. And I can study limits just as before. We know that, if I'm away from Tc and in infinite volume, the correlator actually falls off exponentially. So there's an e raised to minus r by xi sitting here. Similarly, on the other hand, if I'm, at lattices which are too small compared to the correlation length, then it must go like this so that it basically removes this fall off. This on a finite lattice, it cannot really go to 0. You see, these are some results we have on some small lattices. It doesn't fall off to 0. It just saturates. And then if I increase the lattice a little more, it falls a little more and then it saturates. Falls a little more and then it saturates. This is basically because the correlation length is already like, it's 2.2692. It's already maybe of the order of 1000. So yeah, that's the second limit. In fact, it predicts that, this saturation plateau must somehow decrease as L to the minus eta, and some quick tests seem to confirm that, this is just the case. Yeah, this was just a rough fit that I did yesterday, and you see that you get something like eta equal to 2.45. We know the exact value is 0.25. It's almost ballpark, say up to 1.5 sigma or so. And I think it's pretty good for rough calculation. So anyway, before, we end up with this nice looking, finite size scaling prediction. And we can do the same thing. If I plot L to the eta times G2, or even for that matter R to the eta times G2, they should fall right on top of each other, provided again we use the correct values of Tc, nu, and eta. One thing, of course, is that G2 is now a function of two variables. So instead of curve collapse, you're actually going to have surface collapse, which is not something you can see or plot. So what we did for this was we fixed. And we could do this because, we know nu, it's 1 for the two-dimensional Ising model. We also know Tc. That was what we were actually interested in. So we took Tc and nu as inputs and tried to vary eta so that we could get a kind of curve collapse. And well, yeah, when we put eta equal to 0.25, we actually see that all those correlators that I had before were showing, widely different behaviors. They all fall on this band. Actually, the width of the band is actually just because of the error bars that you have, these 2-point function. If we were to probably run our program for much longer, we would actually probably be able to even shrink this band. And the other thing is that nu, this is what I get when exactly, not nu, sorry, eta exactly equal to 1/4. But I can vary this. Now, this is actually a fat band. So I can actually vary this, let's say, from 0.22 to something like that. And I can, still get a decent curve collapse. So in some sense, it gives me like a kind of confidence region for how much, for my determination. And not just that, if I improve the errors on this, then these bands shrink. And that means I have less freedom in varying eta. So that's, that's the way that's the way we are actually planning to do this and move on to higher order OPs. So in that context,
sorry, because I see some lack of with L.
I'm so sorry.
Is this
one? This is because of the periodicity. We use periodic boundary conditions on the lattice. So if you, okay, so.
No, that was not my issue.
You mean
about you change L. So 800 is blue, is that right?
Yes, okay.
And then 1200 is red, and then 1000 is pink. So as you...
Just a question of statistics. I asked this to my student as well, and unfortunately, within the current statistics, that's what it looks, but I think it's just a question of statistical errors. I think these are really fluctuations in some sense. So you really need maybe like order of maybe 50,000 something, and I think he probably only has 5 or 10,000 right now.
I see.
How do you construct this correlators of the lattice?
Correct. Point. For the 2-point function, you can take the Fourier transform and actually look at it in Fourier space. Now we go to the 4-point function, and here you can't do that. If you take the Fourier transform, you actually have to sum over all the intermediate k values. It becomes n cubed or something. So the thing is just 4 points, sum over the whole lattice. So you automatically get translation invariance because I'm summing all the lattice. And these are just +1s and -1s, so we don't really expect much noise. Yeah. Right. A more straightforward but more tedious procedure would be, like, since you fix t to some non-zero value, get the 2-point function for larger and larger lattices, saturates somewhere. Then you know you have an infinite volume example. Reduce T a little more, fit it. A little more, do the same thing. Now you have to do even larger lattices, and finally you extrapolate to the critical point. That's doable, but you can see that clearly it's more economical. We still need to extrapolate to L to the 1 by nu T equals infinity. You see this is just slightly above L, but some quick seem to suggest that this volume dependence is much less compared to this volume dependence here. So one alternatively, like instead of worrying about the limits, you could probably try and this G2, you could try and calculate this G2 using maybe some RG theory or something, and then you actually can fit it for values of y as small as 1 or 2 instead of very large values. Anyway, so then I said, okay, fine. It was the 2-point function. It was like a kind of cross-check. It told us the method works. So then with Atul and Anirudh and Anindo, we said, let's go on to the 4-point function now. Now, 4-point function, actually things get a little more involved. So let's say I denote these 4 points by R1, R2, R3, and R4. Now, first thing is translation invariant. The Ising model is translation invariant. So it actually reduces these 4 points to 3 differences, 1, 2, 1, 3, and 1, 4. And the other 3 pairs, let's say 2, 4, 3, 4, I can just construct it from sums and differences of R1, 2. Next, if I impose rotation invariance, now it comes down to 6 scalars. I mean, 3 vectors is 3 into D, scalars in D dimensions. But now because of rotation invariance, all I have is 6. I mean, the 3 lengths and the 3 angles between these 3 vectors. So in 2 dimensions, actually this number comes down to 5, but anything from 3 or greater, it's now a function of 6 variables. And lastly, conformal invariance predicts that in fact, out of these 6 also, the only dependence is through the 2 ratios, U and V, which are ratios of lengths. So one way to test conformal prediction, which which we will do in the future, is actually to define widely different configurations, R1, R2, R3, R4, which have the same U and V ratios, and the 4-point function should actually agree. Anyway, so based on all this, if I write something like this, a function of, let's say, 4 into D plus 2 variables can now be written as a function of 7 variables. The 6 scalars, the dots here are the angles, and the length. Previously, we had studied a finite for 2 sets of configuration. We found that it seemed to work for square, but it broke down for strips. So we didn't understand this at first. Then we realized that when a strip of length 1 by L, the angles change as the length of the strip is increased. So that is why the data weren't actually collapsing on each other. But if I have a square of side L by L, all angles are 90 or 45. So we actually played this game for squares, and again, you see again that up to the error that we do have, we get curved again and again. Here, if I need to put the right dimension of delta phi squared from this, from this one which I have really here, you see that actually delta phi squared is predicted to be 1/4, it's 1.
Delta phi is 0.25, but delta phi square is 1.
But then here it would seem to suggest half.
The power is delta by 2, so doubles.
Okay. So okay. Sorry. Right. Anyway, so here the power that I had to put was 1/4 for this. So 2 delta phi was 0.5, which it's off by a factor of 2 from what you defined. But other than that, you get the same curve collapse. The next thing, actually somewhat slightly harder, is to try and extract OPs from the behavior of these collapsed curves near the origin. But that is something we have some preliminary results, but I thought it not wise to put it in here right now. It's still work in progress. But anyway, it seems that you can actually verify these anomalous dimensions, and this is actually something you can even do in 3 dimensions. Now that we have a technique that works, we can even push it to 3 dimensions, and maybe by calculating higher order functions, you can probably even get some higher anomalous dimensions. But anyway, what we found, I mean, what I've shown you here, but what we seem to find is that it's possible, although it's kind of a challenging exercise to calculate OP coefficients and anomalous dimensions. Two of the challenges that we face here, for example, is that, like I mentioned, they're quite sensitive to finite size effects, and we need to be close to the critical temperature. One thing that I didn't mention here is that we had an exact expression for the 2D case, and that kind of cut our work out for us a little bit. In 3 and higher dimensions, it's just a series. It has to extract, match the series with these data and extract the coefficient of interest. But anyway, I mean, we found that finite size scaling was something that seemed to, reduce some of the effort needed, make it somewhat easy. And this is because we actually replaced the conformal prediction, which is an infinite volume prediction, by a finite volume but still rather universal function, which we obtained by rescaling variables. And as you can see, it doesn't matter. It's still quite challenging, primarily because of the error bars and various other systematics. So it's interesting to see how far you can push them, and also how far they will work for, let's say, a 3D Ising or like an ON model, because there are a lot of CFT predictions for these higher dimensional or more complicated models as well. So anyway, that was what I wanted to show you. So thanks. Thank you.
So in the context of 2D, for instance, I can imagine putting stuff in a periodic boundary condition.
Periodic boundary condition.
So that, I mean, I can make, what I'm trying to say is the following, that, maybe, if I put, I'm saying that maybe at t equal to tc itself, I can make the geometry compact by an analytic mapping, by a conformal mapping, and compare that with the lattice calculation. Put an appropriate boundary condition, so that, like even in, I can make that into a sphere, for instance. Well, I don't know how you can put it, or just, I don't know, maybe a torus.
Periodic boundary condition is a torus, right?
Yeah. So therefore, why go away from t equal to tc? Okay, in 3D, but I see you were saying the conformal mapping technique will not be available, but certainly there is, I mean, certainly we can talk about exactly conformal theories on S3. Sphere on the lattice, but T3 will not, so I cannot get, I cannot do analytically a conformal field theory on a T3 and know what the correlators are supposed to be. I don't know the answer to this question. But then there's a whole lot of stuff that will be different. I mean, you just have to put appropriate boundary condition in your simulations, and you can stay at t equal to tc. I don't know whether this is...
Well, yeah, I mean... sorry. Yeah, like... we have periodic boundary condition. So it is a torus. We were more interested in comparing it to, say, R3 or R4.
Yeah, he's saying that you can have the predictions from theory.
Right.
For example, in 2 dimensions, it's like if you use the complex coordinates for the 2-dimensional plane, so then it's 1 over z1 minus z2 mod to the power 2 delta. And then you can make do a map. Z1 is equal to e to the power whatever omega 1, and Z2 is equal to e to the power omega 2, and that will make this stuff from a plane to a cylinder.
Okay.
And then you can do more complicated stuff, which makes it into a torus. Some Christoffel-Schwarz transformation. And you have more complicated formula to compare with, but you can be at t equal to tc. In 3D, I don't know whether this will work or not. But in 2D, certainly you don't have to go away from t equal to tc. You have a nice formula for t equal to tc, but
boundary conditions. Okay.
And what if you want to be as close to the conformal
Consistent big
Mhm.
by repeating periodic.
Yeah. I mean, well, periodic boundary condition, smallest, let's say, finite volume dependence of all boundary conditions, which is why we use them. Of course, we wanted to get to the infinite, like let's say, infinite volume limit very quickly, in which the boundary condition doesn't really matter. So that's why we were using periodic boundary condition, but that means we're already on a torus in some sense. So.
Your formulas have changed. It's not 1 over R1 minus R2.
Right, they would of course have to now be periodic in the circumference of the torus. Right, I mean, it cannot, I mean, if the torus has a circumference C, it cannot really fall off.